Hello everyone. Today we'll be talking about some additional features of X-Array. So let's start out by installing, if you haven't already, and then importing the X-Array module. So the first feature I wanted to talk about is interpolation, and we saw through indexing with the cell and the iCell methods for X-Array objects, that is data array and data sets, we can select a single value or a subset of values. Now, we also did see that if the label or index value is not available in the X-Array object, then we're going to get an error. So let's take a look at how we can get that error. So let's start out by setting up the coordinates in the X-Array, and then just setting the values at x squared. So here we have 0, 1, 4, 9, and so forth. Now if we plot this data, here we go, and we put a marker, and again the plot method of the X-Array object has all the attributes that matplotlib provides. Now if we ask for an x of 4.5, we'll see that we'll get an error because we only get an x coordinate of 4. So let's prove that, and here we go. So one way to get around this is to use the interpolate functionality of X-Array, and that will give us here 20.5. So if we go back, we'll see that from the 5th to the 6th element here, so we're at 16 and 25, so our value is between there, and it will do a linear interpolation in between. Under the hood, it uses the module interpolate by SciPy, Scientific Python. And so there's additional options that we can use. So let's try out first to create a new set of coordinates. So let's take the original coordinates x and add 0.5 to them. And what we're going to do is we're going to generate two new arrays, one of them using the linear interpolation, one of them using the cubic interpolation. And then we're going to plot all three and just adding labels here. So the only thing we did is we set the new x coordinates, and we specified the method. You can see that they're pretty close, the orange and green line, and you can see though that the blue dots at the beginning and the end don't have data for the green and orange interpolations because again we shifted the x's by 0.5. Now let's take a look at the group by functionality, and we covered that over pandas. We talked a little bit about it with X-Array, but now let's do something where we're loading up the sea surface temperature monthly mean data from NOAA. The other thing we're doing here is, so we're setting the URL, we're opening the dataset. There's some additional variables that we don't really care about. One of them is called time band, so we're just going to drop it. And then we're going to select the time series from 1960 to 2018 and just make sure that the data is downloaded with a load method. So I'm just going to pause the recording just to because it might take a while for the data to download. And we're back. So data downloaded. You see that we have some data here. We have the longitude and time dimensions. So let's first of all select the first just use a single index here, and if you remember from NumPy, if it's a multidimensional array and we use a single index, it will just go by dimension. So just a single index will pick the first dimension, so time. So this will pick out the first time, which should be January of 1960, and we can plot that up. Now one thing we'll see is that because now the dimension in this DSSST 0, the dimensions are now a single time dimension, but they're not long. X-Array will know that it needs to create a spatial plot. On the other hand, if we select a specific latitude or longitude point, now the only dimension that's left out that's not 1 is the time. So now this will instruct X-Array to use a time series plot. And there it is. Again, the niceties that we get from X-Array is that we get the labels, We get a title, we get the correct time series, axis labeling, and so forth. All right, now let's take a look at something slightly different, but still within the theme of the group by. So we can see how we can group by different things. So far, we've looked at how we can group by separate values or keys, as we did in pandas. Now, some additional things that we can do with Xarray is using specific aspects of the metadata. And in this case, we're going to be looking at the time dimension and some additional things we can get there. So if we look at the ds time, let me take this out, see that we get the time. It's a date time array, but it provides an extra accessor, just like pandas does. This one has a few more powerful features. Here you can see the objects, a datetime accessor here from Xarray. Now we can get the month, we can get the year, we can get the day, and so forth. What this will allow us to do is use this to split our array. So for example, if we're trying to get monthly climatologies, which we will do in a little bit. In monthly climatologies is just taking, for example, all of January's and taking the mean, the max, the minimum value of that. So all the Januaries in the entire time series, all the Februaries, and so forth. So this is the type of labeling we want. So if we group by, you see now that we get the month, and we get 12 groups, as we would have expected. So now we can map an operation on the group by object. And let's take the mean, and we say take the mean over time. And there it is. And we're getting an array where we drop the time dimension, but we get the month dimension. So we can use this SST_MM, which is a monthly climatology, and we can plot at the same location as we did before. And there it is. So these are the average temperatures for each month for the entire time series. One other thing that we can do is something called a zonal mean climatology. So that is a spatial plot, but not on both dimensions, not long. It's sort of a spatial plot with a time dimension associated with it, and time here would be the monthly climatology. So let me just comment that out so we can see what we're getting. So if we get the mean with the dimension over the dimension longitude, you see now that we drop from 3 dimensions to 2 dimensions, month and latitude. If we do not transpose it, and I won't do that, so let me just cut this. There we go. So let's say that we plot a contour, and the contour has some keyword arguments, how many levels, the minimum and maximum values that we can use. Here you can see that we get latitude on the x-axis, month on the y-axis. Now, latitude goes from north to south, so it will probably look better if we just had latitude on the y-axis. Hence why we'll transpose. And there we go. So now we get month on the x-axis and latitude on the y-axis. And that what it does is just flips the dimensions essentially. Alright, and then let's take a look at the mean of the mean climatology, but then look at the difference between 2 months, the March and September climatologies. And then we're going to plot them. So with this here, we're just calculating the difference. And there we go. Again, as you can see, we can really just use the select, pick what we need after we've calculated the monthly climatology. So really perform something that could have been relatively complicated, and do it in a couple of lines of code. And again, this is typical analysis that we do in the climate or earth sciences or environmental sciences for that matter. Okay, so in the hands-on exercise, what we want to do is we want to calculate what's called an anomaly. An anomaly is essentially the variability, so it's the difference from the mean. So we would subtract the mean. So for Januaries, we would subtract the mean of all Januaries. So we would get, how a specific January, let's say in January 1960, how much warmer was it, or how much colder was it than the average. The way we can do this is by grouping by the month. But in this case, we're going to subtract then the monthly climatology. So what we're doing here, and let me comment this out so you can see what the naive implementation would have been first. So first thing you might think about is saying, oh, well, I'm just going to subtract SST from SSTMM, right? So we're getting the sea surface temperature. And I forgot, sorry, the SSST. Now what's happening here, you see that we're getting 4 dimensions, and that's not what we expected. So we get time lat long, but then we also get the month. So that's not exactly what we're looking for, because we're looking for the anomaly, so we're looking for time lat long only. So the way to do this would be to group by the month. So essentially what this will do is it will create those 12 groups and then subtract the SSTMM from each one. Now, because SSTMM has a month index as well, or month dimension, similar to pandas, X-ray will align those dimensions and the values. So then the correct month climatology will be subtracted. So the Januaries will be subtracted from all the January data. So let's take a look at that. And here we go, time lat long. What do we expected? So if we plot the anomaly for a specific location, the same one that we used before, you see now that the values now become from minus something to plus something, but close. So we see how we see a warming trend here, and that's the purpose of anomalies, essentially, to look at trends. Another thing we can do is we can look at the global map of the difference between January 2010 and January 2016. So the first thing we could try to do is this, SST anom, time. Now that's going to give us an error because we're going to get a 0 time dimension. And the reason we're seeing that is because if we go back to look at, hold on, deleted that. Okay, so let's look at SST anom. See that we have this time lat long, but we got a 0 dimension when we selected this. So let's take a look at our time, and you see here we've got the the dates set with 1960-1-1, 12-1. So this is not going to work exactly if we just select that month. So we have to actually select the actual date. So we would have to do 1 and 1. And now you see that we got the right lat long without the time dimension added to it. So we can plot this, and there we go. So for January, we see the difference between 2010 and 1960, and best by plotting the difference between the anomalies. Okay, last one before we get into the final hands-on exercise is the resampling capability, which also translates to what's called a rolling operation, which is a moving window operation. So we get a moving average, for instance. So similar to pandas, this works pretty much the same way, but just be careful about adding the correct dimensions in each call. So for instance, we can take the data set, resample it every 5 years, but again, we have to specify the dimension. And the 5Y will make sense only if it's the appropriate dimension type. So if we did lat 5 years, it wouldn't make sense, right? So anyway, and then we take the mean, So let's take a look at what happens here. And you see that we get, because it's every 5 years, so from the original, which had, let's take a look, 708 times, divide by 5, we're getting 13, as many years as are available to it. So rounding out. So we can do this sample. Then we can do plots. We can do all kinds of things that we did before. And for example, we can resample this and then take the difference between January of 2015 and January of 1965. Now, one of the things that's happening is that depending on how you set this time specifier here, you might get a different date. You might get, because for example, if you did, a BY, you're going to get the beginning of the year. If you did Y, you're going to get the end of the year. So one thing we can do is we can select the nearest date. So we use the method nearest, which under the hood is going to use the interp functionality that we saw from before. So we take the difference, we take the SST variable, and we plot it. And here we go. And again, you see how easy and quick it is to do all this analysis and actually get a visualization out. Resampling, you saw that we go from many time steps to fewer time steps. The moving window operations actually will give us more time steps than the resample operations, because we are performing an aggregation over windows. So we're going to get, for example, if we select 12 times, so essentially it would be an annual, and some additional keywords that you can look up at the doc string for. We take the mean of that. You see now we're getting 708. So for the first 12, they're going to be empty maps, because again we're only going to get a value for the 13th or the 12th map, where we get the average of the previous 12, and then for the 13th we get the average between the 2nd and the 13th, and it continues along until it reaches the end of the time step. So that's why we get the original dimension back. All right, so let's do some plotting here, where we can plot the SST for us for our location, and then we're going to do the resampling and the rolling. And there we go. So you can see here that the 5-year resample, the 12-month rolling mean, and the original time series. And you can see how this very significant smoothing, actually how it reduces the variability by a lot. All right, let's move on to the hands-on exercise. So here we're going to reproduce this figure that shows us the sea surface temperature anomaly in the El Nino region. So there's an indicator in the index that we can use to characterize whether we have an El Nino or La Nina year. So if the values are above this red line, we have El Nino. If they're below this line, so if it's a cold anomaly, then we have a La Nina. So the way to calculate it is to select a bounding box, so the region between plus or minus 5 degrees latitude, 170 west to 120 west longitude. So we get the warmer cold phases defined by 5 consecutive 3-month running mean of sea surface temperature anomalies in the Nina region, above the threshold or below the threshold. So you see the 0.5 here or the minus 5. So if we had 5 consecutive 3-month running means, and that's a rolling operation, then we have El Nino or La Nina. So we're going to load up the data from here, drop the time bands variable, and extract the data. So we're going to do this by loading up the data the same way that we've done before. So let me see here how we can do this. We're going to copy the link and let's take a look at that. And then remember that we're going to drop variables, and going to drop the time bands. Let's take a look at DS. I'm going to pause it. Oh, actually, no, it downloaded quickly. Very nice. All right, so we get our data here. We get, lat long, time. We go from 1854 to 2023 in this case because it's the newer data set. So, we can decide to pick up only 1950 to 2020. Doesn't matter. We can, or we can generate the updated one. That's not a problem. So, first things first, we're going to calculate the climatology and the anomaly. So again, similar to what we've done before. So let's calculate the anomalies, or first let's get the, we can calculate the climatology in one go. So that we have, actually, you know what, let me just SST, instead of typing DSSST all the time, let me just do this. And one thing we want to do, actually, let's do it again in one go. Let's select the region, the Niño region. So that's between 5 and -5, right? So let's do lat. And we're choosing 5 to -5 because, again, you see that it's north to south. And then let's, oops, forgot the slice. There we go. Slice 120 west to 170 west. And actually that's not going to work. So it would have to be this, but we can see that the longitude is actually from 360, from 0 to 360. So then we just have to do 360 minus 120 and 360 minus 170. So actually we need to be looking longitudes 190 to 240. All right, so that will give us the SST. See here, 5 latitudes, 26 longitudes. So let's calculate the anomaly. So it would have to be group by, and then time month. And then we will subtract the SST group by time month. Whoops. There we go. And then we're going to take the mean over time. All right, now it's calculating. So now it's downloading the data because, again, lazy evaluation. So we need the data. So let me just pause the recording, and then I'm going to come back when it's downloaded the data. All right, and we're back. We have our anomalies here. So now we're going to plot the data. So the first thing we're going to do is, well, we need to get the mean, the average over the entire domain over time. So we're going to get anomalies, mean over latitude and longitude. And what I'm going to do here to make it a little bit easier, I'm going to convert it into a pandas time series. It's going to look like this. Again, make things easier. And also what we're going to do, let's do this here. We're going to select slice from 1950 to 2020. As you know, that's what we were. Oh, my bad. So I can't do this. So I need to do it as a string. There we go. All right, here we go. I've got that. Now let's generate a plot. So we're going to first create the figure and the axis plot. So let's do PL subplots, and then we can do 1, which we can skip, of course, but and then set the size to 14 inches by 8. And then what we're going to do is we're going to use the axis object. So now let's take a look at the plot again. Okay, so we need these filled lines here. So we need the line and the area filled in between. So we're going to use the matplotlibs function that's called fill between. So let me just generate this plot first. Okay, so now when I hit tab, there we go, fill between. So fill between takes the x-axis value, so that's the index, the time series, and remember that we want to create an orange from 0 to whatever value is O and I. So then we're going to say where O and I is greater than 0, and then we're going to set the color to orange. Okay, let's try to do the same thing, but now for negative values. So it would be from, again, 0 to O and I, but where the O and I is less than, and we're going to use cyan. That's the cold. So let's see what we get from these. Perfect. Again, very nice function to be able to create these types of ribbon plots. Now, remember that we also need the rolling mean, the O and I 3. So let's do O and I rolling 3 months. Take the mean. And the reason I generate pandas is because I knew we were dealing with time series, and I just didn't want to type the dimension names all the time. So again, just makes things a little bit easier. So one thing we're going to do now is we're going to plot, let's take a look here. Okay, we're going to plot the 3-month running mean, 3MTH running mean, and that's a black line. So let's plot this. So X, plot O and I 3 index, O and I 3, and then let's set the color to black line. Let's set the label to 3MTH running mean. All right, let's take a look at that. There we go. It's coming together. So next, we're going to do the thresholds. So the thresholds are going to be just straight up lines. So, again, we're going to use the O and I index, and we are going to use the 0.5. So there's a couple of different ways we can do this, either with NumPy to generate the array, or simple, just take a list and just multiply it by the length of O and I, which means that it will just replicate that. So we're going to do color red, and we're going to set the line style to dash lines, and we're going to set a label, which is, let's see, it's El Nino threshold. El Nino threshold. Let's do the same thing now with a -5 with the La Nina threshold, and now let's take a blue color. So La Nina threshold, there we go, blue. Okay, so that's good. Much better. Now I really don't like these gaps here, so what I'm going to do is I'm going to set the limits xlim, and I'm going to set the limits to PD time. Oops. Hold on. Let me import the pandas module because we're going to need to create this into a timestamp. So import pandas PD. There we go. Let's go back. Alright, so PD timestamp. And we're going to use the first value of the index, O and I index here. And the last value is going to be PD timestamp of O and I index -1. Alright. Okay, better. Alright, next thing, I think we just need to put the X label here. So X set Y label. Let's put, what is it? Anomaly in degree C. There we go. Anomaly in degree C. Fantastic. Oh, and then the last thing we need to do is add a legend. Now, we could, actually manipulate it to add it here on the outside the plot, but then we would have to create a new access object, so it's not really that important, so it's not identical, but we're gonna just add the legend here. And that's it. So again, you see that with a few lines of code, we can create a fairly complicated plot. Alright, and then now this generated time series that has true or false for positive or negative El Nino phases. So one thing you remember is that wherever the running 3-month mean is greater than 0.5, a threshold, then we have to set true. So what we're going to do now is we're going to, let's just copy the ONI3 array, so we don't, because we're going to put 1 and zeros to us for true or false. So let's start with, oops, and so set it to 0, and then wherever Enzo is, wherever ONI is greater than 0.5, we're going to put 1, and Enzo ONI3 less than 0.5, we're going to set that to 1 again, because again we're only looking for either positive or negative. So if it's an Enzo phase, we're looking for that. So remember also that if we need to have, so if it's a 5 consecutive 3-month running mean that are above or below, okay? So the phases, remember now, we're going to have ones wherever we have greater than 0.5 or less than minus 0.5. So if we want to have 5 consecutive ones, if we can calculate the rolling sum of these ones and zeros, okay, so we can do rolling 5 and take the sum. So if this sum is somewhere, if it's 5, then that should put a true, right? Or a false if it's not. So wherever there's a true, so let's take a look at phases, and there it is. So again, we create an array that has zeros everywhere, and then says, oh, the value of the 3 running mean of the ONI index is above or below the threshold. Set that to 1, and then if we take the rolling sum, that means that there's 5 consecutive ones. So this will give us true, will evaluate to true or false, and it will put it into the phases time series. So we can also plot that one up. Oops, what happened? No numeric data. Oh, okay, fine. Because it's true or false, it doesn't know how to plot them, so we're just going to convert it into as type int. There we go. Okay, so as you can see here, we're getting where it's 1, we have either a linear or La Nina. Where it's 0, we don't have anything. And that's about it. I will, well, I will have another recorded lecture on Thursday. We're going to be talking about Python parallelization. And I will see you next week.